quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
So today we're going to be looking at properties of electromagnetic waves. We've got a few to get through, and the first is that electromagnetic waves are formed from oscillating electric and magnetic fields. You know from previous work what electric fields and magnetic fields are. Electric fields are the ones from electrostatics, static electricity, and magnetic fields are from magnets. So let's imagine that we have a wire and we have a current in the wire. And what causes that current? Well, the current is caused by electrons moving up and down the wire. And if we draw a graph of how that electric charge is distributed in the wire, for our example here, it will be a simple sine wave. So our current in the wire forms a sine wave. And this axis here is our time. The y-axis is the current. So our current I induces an electric field. As the electrons move, the excess of electrons in some areas produces an electric field, just like static electricity. And we call that electric field E. And we put a little line over it because that's a vector field, or a field of vectors. And we know that constant current causes a constant electric field, and we can measure that having a varying current will cause a varying electric field around our wire. So let's draw our electric field strength on top of our current strength with respect to time, and those will be closely matched because the electric field is generated from the motion of the electrons. And these lines we're adding here show the strength of the electric field at each point. One thing we may not know yet is that a varying electric field generates a magnetic field at right angles to it. This is something that we can test experimentally. We call our magnetic field B, and that's also a vector field, so we put these little arrows over them to symbolize vectors. As we said, the magnetic field is at right angles to the electric field. So let's draw that on our graph as well. We put another little axis in at right angles to the first two. That's our magnetic field axis. And at each point in time, the electric field will produce a magnetic field of a corresponding strength. And as the electric field swaps polarity, the magnetic field swaps polarity too. And now we'll just draw in our magnetic field and show how it varies over time as a sine wave, just like the electric field does and just like the current does. Now, if we move out into space, far from our source, we plot our electric field and we plot our magnetic field. And now instead of plotting time, we're going to plot distance. that should be distance. There we go. Now here's our electric field vector, and at right angles it produces a magnetic field vector. And again, our next electric field vector produces another magnetic field vector at right angles. And what we also need to know is that a changing magnetic field will produce an electric field at right angles, just as the electric field produces a magnetic field. So one produces the other, produces the other, produces the other. And if we draw the graph of our electric fields and magnetic fields as they induce each other at right angles, we can see our graph developing. There's the electric field produced by the magnetic field changing, and then as that electric field changes, it produces another changing magnetic field. And so on. And so on off into space. So there's our electric field in red and our magnetic field in blue. And what this means is that because the electric and magnetic fields create each other as they change, our wave continuously propagates through space. And as long as it continues to travel through the same medium, such as a vacuum, it will continue along at the same frequency and the same wavelength, and indeed the same velocity. Now let's go to Google and look for some nice pictures. A quick search will show you that there are plenty of pictures of electromagnetic waves around. Hundreds and hundreds of them, in fact. Let's just pick one at random, see what that looks like, and there you go. There's a nice picture of the electric field and the magnetic field at right angles to each other. And here's an animation from YouTube, just showing you the author there. And this shows you quite nicely how the electric field and magnetic field are constantly varying and constantly at right angles to each other as the electromagnetic wave travels through space. Now let's just cut out this diagram. We're going to need that for the next section. We'll get rid of everything else and move that over. And when we studied sound waves and mechanical waves, we learned that they need a medium, such as air or water or springs, to travel through. And in fact, those waves are deformations of their mediums. But with electromagnetic waves, even though they travel through substances, they don't actually require a medium to travel in, so they can travel through vacuum. The next question is, how far can they travel? Well, let's have a look at our point source of light and draw lots of little rays coming out. Now let's have a look at one ray and extend it outwards. And now we'll extend a second ray. And let's say that these waves travel for a distance d, and d tends towards infinity. The two waves are separated by an angle alpha. And as we travel further away, the intensity of the light drops off. And we know that from simply watching how a light globe fades as we get further away. But the individual rays travel for infinity, because so long as those electric and magnetic fields are changing and creating each other, they'll just go on doing so forever and ever. The electric field creates a magnetic field, that creates an electric field, that creates a magnetic field again, and so on. So what we say, therefore, is that electromagnetic waves undergo self-propagation and have an infinite range, until, of course, they bump into something. The next question is, what speed do these waves travel at through their infinite range? Well, of course, the speed that they travel at is the speed of light, and in physics we call that c. Looking at our wave equation, we know that the speed of a wave will be equal to the frequency multiplied by the wavelength. Now, in a particular medium, that speed is going to be constant. And that means that any wave, like a sound wave or a light wave or a spring, will travel at the same speed in a particular medium regardless of its frequency. So sound that is a very deep tone will travel at the same speed as a very high-pitched sound. And the same is true of light. As it travels through any medium, the velocity remains constant. And so we know then that if the velocity is constant, the frequency must be inversely proportional to the wavelength. So if the frequency goes up, the wavelength must go down, or the wavelength must get shorter for a higher pitched sound or for a higher frequency light wave. Now, a couple of hundred years ago, a very clever physicist called James Clerk Maxwell was looking at how electric and magnetic waves propagate in space. And he started out with just the electric field changing in space and the magnetic field which was induced by it and also changing in space. So electric field causes magnetic field, causes electric field, and so on. And then he did lots of very clever and very hard maths, and at the end of it all he formulated what are now known as Maxwell's equations, a set of equations that describe all of electromagnetic radiation. And very surprisingly, he found that the speed of this electromagnetic radiation was equal to 3 by 10 to the 8 meters per second, which people already knew as the speed of light. And this was great because until then nobody actually knew for sure that light was an electromagnetic wave. It was suspected, but nobody knew for sure. And this work by Maxwell finally proved that light was in fact an electromagnetic wave. Once this had been determined, predictions were made that other sources of electromagnetic waves would be found, and that's how the existence of radio waves was predicted well before their discovery. Now we're going to look at an aspect of waves called superposition, which means adding together. Now we've already looked at superposition when we studied sound waves. So if we have a speaker, the sound coming out of that speaker can be a simple sine wave, or it can be a collection of waves of different frequencies. Some of them may not even be sine waves, all added together to produce a very complex sound. And when we draw that graph, we get a very complex sound signal coming out of our speaker. And that's how we get complex waves from things like musical instruments. The same thing happens when we add electromagnetic waves together, when we add light of different colors together. So if we start with our wire and the current running through it, and we get our simple sine wave, we call that a monochromatic wave, which means one color, and that's just like having our simple sound wave. And in that monochromatic wave, we've got our electric field and our magnetic field at right angles to each other, and they are all simple sine waves. Now, if we draw another wire and we have a very complex current running through the wire, then we'll also have a very complex electric field running through the wire and a very complex magnetic field. We won't draw the magnetic field this time, it's too complicated. And we call the result of that polychromatic, which means many colors. So we have electromagnetic radiation made up of many different colors of radiation. So we have electromagnetic radiation, or light, made up of many different colors, all joined together. And this is how we get complex electrical signals in communications. So if we go back to sound, our example is music, whereas for electromagnetic waves, our example would be a radio wave that carries music on it. Now, even though we said that electromagnetic waves don't need a medium for propagation, such as sound needing air, we still have to be aware that electromagnetic waves are affected by different materials. The properties of mechanical and sound waves also apply to electromagnetic waves. So we have properties like absorption and absorption, reflection, where the wave bounces off a barrier, and also refraction, where our wave enters a material of a different density and changes speed, which changes the angle at which the wave travels. Now, even though the speed of light in a vacuum is constant, the speed of light will change whenever that light wave enters a new material. So light travelling through glass, for example, travels at a different speed than it does through a vacuum or air or water. And for waves that travel through metals, they also travel at different speeds. All of these materials react differently to electromagnetic waves at different frequencies. As an example, let's look at the microwave oven at home and the door of that microwave oven. You know from your own experience that when you're cooking something in the microwave oven, you can see through the door, but microwaves can't come out through the door. If they did, they'd cook you while you were watching it. So that tells us that different materials react differently with different frequencies of electromagnetic radiation. Another classic example of that is the refraction of visible light through a glass prism. So we have white light shining into the prism and light of all different colours coming out of it, just like a rainbow. And as we know, this was first demonstrated by a very famous Englishman called Isaac Newton, and was made even more famous by another Briton, Pink Floyd. The next topic is how we detect electromagnetic waves. Now with sound waves, our source is a speaker, and we detect those waves using a microphone. The sound waves move the air, and the air jostles the sensor on the microphone, which sends a signal to our amplifier. With electromagnetic waves, we have our wire, which carries a current. The electrons move up and down, creating an electric field that varies, and that gives us our electromagnetic wave travelling through space. At the other end, we have another wire, which we call our antenna, and that too has electrons in it. And when our travelling electric field hits that wire, that electric field moves the electrons in the wire up and down, and the movement of those electrons is measured as an electric current in the wire. So just as the wave was created by a current moving in a wire, we can also detect that wave at our antenna because it induces a similar current in the wire. It's very important to note that the frequency of the current at our source is caused by the frequency at which the electrons are jostling up and down. That frequency will be the same as the frequency of the electromagnetic wave that's produced, because the wave is produced by the electric field that's created by the varying current. Similarly, at our antenna, the frequency of the current that we detect will be the same as the frequency of the electromagnetic wave and the frequency of the source current. We call this our induced current.
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed
previous work what electric fields and magnetic fields are. Electric fields are the ones from electrostatics, static electricity, and magnetic fields are from magnets. So let's imagine that we have a wire and we have a current in the wire. And what causes that current? Well, the current is caused by electrons moving up.
Now, be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
So today we're going to be looking at properties of electromagnetic waves. We've got a few to get through, and the first is that electromagnetic waves are formed from oscillating electric and magnetic fields, from up and down the wire. And if we draw a graph of how that electric charge is distributed in the wire, for our example here, it will be a simple sine wave. So our current in the wire forms a sine wave. And this axis here is our time. The y-axis is the current.
this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now.